In our discussion of the geometrical structure factor, we have encountered this integral of the electron distribution and j of rho e to the minus I g dot rho, where g is the reciprocal lattice vector. Rho is the relative position vector of the jth atom with respect to the detector, and it's an integral over the cell. This was called the atomic form factor of the jth atom in the basis. And with that, the geometrical structure factor was sum over j from 1 to s fj e to the minus I g dot rj, where rj was the position vector of the jth atom of the basis with respect to the corner. Now, in this video, we're going to concentrate on what this atomic form factor really means and what determines the atomic form factor of an atom. And having said that, if you have identical atoms in the lattice, we should always use the same atomic form factor for each atom in the basis. Okay, so let's start this discussion with reviewing again what the atomic form factor was. It's the integral over one cell nj of rho e to the minus ig dot rho dv. So nj is the electron concentration of the jth atom as a function of its position with respect to the detector, exponential minus I reciprocal lattice vector dot product with the position vector. Now, this is actually the scattering power of an individual atom in the unit cell. So remember, the incoming X-rays are going to interact with the electron cloud. Therefore, the scattering power of the individual atom will be determined by the exact electron distribution around the nucleus. It involves the number and distribution of atomic electrons. It involves the wavelength lambda because the g vector is the delta k vector, remember, according to von Laue diffraction condition, and also the angle of the scattered radiation because of this dot product between g and rho. So once again, this is our setup. For example, if we have a two-atom basis, one atom at the corner, the position vector of the atom with respect to the detector is r. The position vector of the second atom with respect to the corner is rj, then rho equals r minus rj is the position vector of the detector with respect to the jth atom, or we can reverse the direction. It would be the position vector of the jth atom in the basis with respect to the detector. Okay, so rho equals r minus rj, and let's say that rho makes an angle theta with respect to our reciprocal lattice vector g, so that our dot product g dot rho will become the magnitudes g rho and cosine of the angle between them. And for simplicity, I'm going to assume that the electron distribution is spherically symmetric. Okay, now if I have spherical symmetry, so here is our rho vector, the position vector of the jth atom with respect to the detector. Let's say that this makes an angle theta with respect to the z-axis. Therefore, I'm assuming that my g vector is on the z-axis. So this is my g vector. G dot rho was g rho cosine theta, remember? And the projection of the rho vector onto the xy plane makes an angle phi with respect to the x-axis. So there is the polar angle and azimuthal angle we have to consider. So what is the volume element in spherical coordinates? Well, if you look at the projection of the rho vector onto the xy plane, you will get rho sine theta. So rho sine theta, and if we multiply this with the angle d phi, this will give us the arc length rho sine theta d phi. And on the other hand, if we vary the angle theta, we would have rho d theta. That would be in this direction, rho d theta. And if you vary rho, you would have this d rho here. So we can basically think about the volume element as consisting of a parallel piped or a cubic region where we have the edges set up as d rho, rho d theta, and rho sine theta d phi. Okay, so this is our arc length. So let me show it here. This is rho sine theta d phi. So basically, if we complete this setup, we would have a volume element that is built like this. So you would see that you have a volume element here. Okay, so this is our dV. So that dV is equal to rho sine theta d phi, rho d theta, and d rho. Okay, so let's erase this because we have made a mess here. Okay, so those are the three elements we have to consider: rho d theta, d rho, rho sine theta d phi. So the volume element is rho square sine theta d phi d rho. Now I see that sine theta d theta can be written as minus differential cosine theta. So because cosine theta derivative with respect to theta is minus sine theta, so it's minus sine theta d theta would give me d cosine theta, so I need a minus sign. So in order to cover the full sphere, we have to have theta ranging from 0 to pi, so that d cosine theta would go from d cosine theta, which is 0, cosine 0 is 1, and then you would have cosine theta becoming minus 1 when theta is equal to pi, and phi ranges from 0 to 2 pi, so this would cover the full sphere. So with that, my atomic form factor would become 2 pi integral. The theta angle is varying from 0 to pi, giving me a variation in cosine theta. So basically, this is cosine theta variation from 1 to minus 1. And rho varies from 0 to rho, and phi does not belong to this integral. So this integral over phi from 0 to 2 pi. So integral 0 to 2 pi d phi gives me 2 pi. So that's where this 2 pi comes from. So 2 pi integral from 1 to minus 1, integral from 0 to rho, and j of rho, e to the minus ig rho cosine theta, rho squared d rho minus d cosine theta. So if I operate the minus sign here, I can change the places of 1 and minus 1. So this integral would be from minus 1 to 1. Then the minus sign is taken care of. And 2 pi integral from 0 to r, well, basically I'm assuming that the electron concentration is 0 for the radius capital for rho that is greater than capital R. Basically that's the radius of the atom. Okay, and so with that we have the integral from 0 to r, integral from minus 1 to 1, and j of rho e to the minus ig rho cosine theta, rho squared d rho d cosine theta. Now we can recognize here that cosine theta can be called u, then d cosine theta would be du. So if I substitute that here, I would have e to the minus ig rho u. For d cosine theta, I would have du. And since I called u equals cosine theta, it varies from minus 1 to 1. And then I have rho squared d rho and rho from 0 to r integral. So this integral from minus 1 to plus 1 gives me minus 1 over ig rho e to the minus igu from minus 1 to plus 1. So if I substitute the end limits, e to the minus ig1 minus e to the minus ig minus 1 gives me e to the plus ig rho. So these two will give me, basically using Euler's formula, for e to the minus ig rho, I substitute cosine g rho minus I sine g rho. For e to the ig rho, I substitute cosine g rho plus I sine g rho. but because of the minus sign, I would have minus cosine 0 minus I sine 0. Cosine zeros will cancel, and I'm left with minus 2I sine 0, but because I have a minus sign at the beginning, so the minus sign disappears, so I have 2I sine 0 divided by I g rho. So therefore my integral, because I have this additional 2 here, this 2 pi becomes 4 pi, the integral becomes 4 pi from 0 to r and j of rho squared d rho sine g rho divided by g rho. Now, if all the electrons were concentrated at rho is equal to 0, okay, so g rho is equal to 0. As rho goes to 0, g rho would become 0. So the limit as rho goes to 0, sine g rho over g rho, it's a 0 over 0 problem. It's the limit as rho goes to 0, sine theta for small angle theta is, so sine g rho is approximately equal to g rho as g rho goes to 0. This is from Taylor's expansion of the sine function. So g rho over g rho is 1. Therefore, in that limit, this part becomes 1. So then my integral becomes fj equals 4 pi from 0 to r and j of rho squared d rho. So what does that give me? It gives me the number of electrons in the atom. So therefore, I would have the atomic number Z. So total electron concentration integrated over the full volume gives me the number of electrons in the atom, and the electrons are residing at rho is equal to 0. That's what I assumed. So if you look up values of F, the atomic form factor for different atoms, these actually can be found in crystallography books. So if you want to do an actual calculation for the crystal diffraction relative intensity of the diffraction peaks, you would need this value. Or we can propose the following. We could talk about a uniform electron distribution inside the sphere with radius r. So let's consider a uniform electron distribution. So going back to my atomic form factor written this way, with assuming a spherical distribution of electrons, basically instead of nj of rho, I can just substitute n here. So it's a uniform distribution. It's independent of the position. So it's 4 pi n. Integral from 0 to r sine g rho over g rho squared d rho, but rho square and the rho in the denominator cancel, so I'm left with sine g rho over g rho d rho. I'm going to call g rho beta, so g d rho becomes d beta. So if I substitute that here, this would become sine beta, and then I would have for rho beta divided by g, and for d beta I would substitute for d rho I would substitute d beta over g, and then I had already a g here in the denominator. So 4 pi n over g, so that's the g I had initially. Then I have integral from 0 to, so because I'm turning from rho to g rho, when rho is equal to r, beta is equal to g capital R, so it's integral from 0 to g capital R, sine beta, beta over g, d beta over g, so therefore I get a g cube in the denominator, 4 pi n divided by g cube, integral from 0 to gr, beta sine beta d beta. In order to perform this integral, we can use integration by parts. I call beta u, and I call sine beta d beta dv, so that v is minus cosine beta and du is d beta. Integral u dv is uv minus integral v du. That's the integration by parts. So if I substitute that here, for the integral, uv is going to be beta times minus cosine beta minus integral v du, minus will become plus cosine beta d beta, and this integral is from 0 to gr. So it's 4 pi n over g cube. The integral of cosine will give me a sine beta minus beta cosine beta evaluated between 0 and gr. So at 0 I will have sine 0, and from beta factor in the second term I will get a 0. So the 0 limit doesn't give me anything, but for gr limit I have sine gr minus gr cosine gr. So if I substitute for the electron concentration the number of electrons in the atom divided by the volume of the sphere, so it's assuming a uniform electron distribution, it would be 3z over 4 pi r cube. 4 over 3 pi r cube is the volume of the sphere. So with that, the 4 pi's would cancel, and I would find 3z divided by beta cube, sine beta minus beta cosine beta, where beta is equal to g times r, is the atomic form factor. Now, I want to consider what happens if I have small angle scattering. So with the von Lau diffraction condition satisfied, k dot g hat is equal to g over 2. With this setup here, you can see that k makes an angle theta with respect to g. 2k cosine theta is g, or we can say 2k sine alpha is g. So theta is the angle of incidence, alpha is the scattering angle. And with that, beta equals g times r can be written as 2kr sine alpha. And since k is equal to, k is the wave number, it's 2 pi divided by the wavelength, 2 pi over lambda, we have 4 pi over lambda r sine alpha equals to beta. Now for small angle scattering, we would have alpha goes to 0, beta is very small. Okay, so because we have sine alpha here in the beta term. So in the limit, as beta goes to 0, what happens to the atomic form factor? Sine beta over beta cube minus cosine beta over beta square. So let's look at the behavior. We would have 0 over 0 from sine beta over beta cube, and 0 over 0 in the second term. So if you take the derivative, you get cosine beta, and from minus beta cosine beta, we can take the derivative with respect to beta gives me cosine beta, and then we can have the derivative of cosine giving us minus sine minus beta sine beta divided by the derivative of the bottom 3 beta square. We're using L'Hopital's rule. So this is a 0 over 0. We're using L'Hopital rule in order to find this limit. So cosine betas will cancel, and one of the betas will disappear, and we will have sine beta over 3 beta. And once again, if we use L'Hopital's rule, this is also 0 over 0. It becomes cosine beta over 3, when cosine 0 is 1, so it's 1 over 3. So therefore, if you go back to your atomic form factor, you will replace sine beta minus beta cosine beta with divided by beta cube with 1 over 3. The atomic form factor becomes exactly equal to the atomic number z. It's the number of electrons. Okay, so for small angle scattering, we find that the atomic form factor becomes the number of electrons, which is z. So in summary, the atomic form factor is the ratio of the radiation amplitude scattered by the actual electron distribution in an atom to that scattered by one electron localized at a point. The atomic form factor is determined by the exact distribution of electrons, their number, and also the angle and the angle of the scattered radiation and the wavelength through this g dot rho. And we have found an explicit behavior of the atomic form factor assuming spherically symmetric electron distribution. We have seen that the atomic form factor takes a rather simple form if we assume this spherical distribution, and especially when the electrons are concentrated close to the nucleus, so when rho is equal to 0. And we can basically, these values are tabulated, but for a simple model, if we assume a uniform distribution of electrons, for example, if you consider s orbitals, right, where we have a spherical distribution of electrons, then we can use the spherical symmetry of the problem, and we find that in the limit, when the scattering angle is there is small angle scattering, the atomic form factor becomes exactly equal to z, and it has this rather simple form for this scenario. And finally, the physical meaning of the atomic form factor is the ratio of radiation amplitude scattered by actual electron distribution in an atom to that scattered by one electron localized at a point.